Okay, welcome everyone to the series, What is Algebraic Topology? So the part of topology which is very algebraic in nature, hence the name. So the main goal is to explain kind of the main concepts of algebraic topology and why they are important. So the main point will be the construction of what is called homology, because homology plays a really big role in mathematics and beyond, as we will see. But in general, topology is a study of shapes. So let's say you have a shape like this. So by what I mean is this shaded region. Then from the viewpoint of topology, that's just the same as whatever this region. I don't want to shade it well. With this shading. So topology is really about the shape of things. And what makes these things equal is that they have a hole here, for example. And what makes them not equal to something like a disk itself is that the disk doesn't have any holes. What topology doesn't care about is kind of geometric aspects, or at least it doesn't care about geometric aspect in general, something like lengths or something like that. Topology is more about the idea of shape. And what is an algebraic topology? Well, algebraic topology is actually a translation. So it turns out that in a lot of cases, topology, so topological data, whatever, is kind of really important. So shape matters. That's kind of the slogan of topology. Shape matters. But it's also very hard. So you would like to translate whatever you want to know about shapes into something you can actually compute. And that's what algebraic topology is doing for you. So you should think about algebraic topology as kind of a translation from topology to algebra. And whatever kind of problem you have on this side, whatever, you just send it to another problem, y, and you solve y, and not this one, right? And then you kind of pull it back, and it might give you information about the original problem x. That's kind of the main idea, right? Why do we want to do this? Because algebra is easy, right? And preferable, we of course would like to have something like linear algebra on the right-hand side, because linear algebra is even easier. But kind of in general, you get some algebraic object. Think of a group, a vector space, and a ring, something like that, some algebraic object, instead of doing some topology-like things, like those guys here. Yeah, and so my picture here of basically of the main fields of topology, just to get us started, is, yeah, well, it's of course a little bit, well, a matter of taste, how you would like to divide topology in what topology is anyway. But let's do it this way. So I have those four things. So I have something on the outside, which is kind of the universe topology lives in. Or in other words, it's the language underlying topology, and that's what you would learn in a class on general topology. Sometimes it's called point set topology, something like that. It tells you what a topological space is. It tells you what, for example, this picture, what connectedness, path connectedness in this picture actually, of topological spaces and all that stuff. There are very nice things you can say in general topology, but for me, it's mostly like the underlying language of what I really like to study. And what I really like to study are more those little bubbles here, which is my funny Venn diagram. Obviously, they have intersections, as you can see, whatever. So the other three main fields of topology, besides the general topology, are kind of the geometric topology, which is the study of manifolds of things like this. I won't do that. I'm going to do algebraic topology, as I said, but think of a knot. Knot theory, for example, would be part of geometric topology. Of course, because you have those huge intersections here, you would also handle certain problems in knot theory using ideas from algebraic topology. And then you have the green one, which is differential geometry topology, which is kind of the idea that everything that looks reasonably like an R to the n, you should be able to do some version of calculus. You should be able to do some topological version of calculus. That is what differential topology is all about. you could think of Riemannian geometry if you read Riemannian manifold, something like that. So some study of certain geometric objects. And then there's a branch I would like to, well, right, the name of this whole series is algebraic topology. So I should tell you something about algebraic topology, of course. And what is algebraic topology all about? Well, it's basically the idea that you would like to study geometric topology or differential topology or something like that. But this is also very hard. So maybe it's better to translate everything into a combinatorial picture or into an algebraic picture. So kind of algebra and combinatorics, I kind of treat them as the same. So everything that is reasonably discrete, I would call it kind of like algebra. So anyway, so for example, instead of having something like this manifold here, which is certainly a nice, smooth, continuous object, or even you are worrying about certain forms of shapes, like this kind of hyperbolic geometry on a parabola, instead of having those pictures, you would more look at kind of shadows of it, some combinatorial shadows. For example, what you see here up here is a simplicial complex. And it's obviously kind of a beefed up version of a graph. So this looks like something you would study in combinatorics. And algebraic topology is now this machinery that takes problems from down here or maybe even outside and translate it into some reasonable form of algebra. So let's actually have a look at the classical example, what you would see in algebraic topology. Just keep in mind, algebraic topology is kind of this translator from something topological, something about shapes, something about geometry, into something discrete, something about algebra, something about combinatorics. So the classical example that you see in algebraic topology is the fundamental group. And it's usually denoted by pi, so pi1. Pi1 and x is some topological space, pi1 of x. So here is x. A very nice picture. I show you some animations in a second. Amazing animations. I'll link the original website in the description. I stole it from there. It's really good. Really nice animation. We'll see it in a second. And the idea is actually you can kind of forget a lot of information that you have about x. So x is the thing I've drawn before. It's kind of this shape with a hole, okay? And the only thing you do is you choose some base point, and that base point doesn't matter, and it's called x0 in this picture. So some base point. Forget it. It's not so important. It's just where everything starts. And what you then consider are loops in this space. So here's a loop, for example. In this space means I'm not allowed to cross over the, I'm not allowed to do something like this because the hole itself is not part of my space. But anyway, I could consider loops like this one or like this one. And okay, that's a huge space, right? You have loops. And then you consider those loops because you're doing topology, you consider them up to deformations. So whenever you have a path of a loop like this, and you have a path of a loop like this, and your space X is in between, you can deform them, and they're actually the same. So you could, for example, my little loop here, you could pull it straight. So you can just pull it out because you have this whole shape here, which is in your green space. So you can just pull it until it's gone, basically. So that's the space you would like to consider. Loops in a given, well, X in a given topological space. And the funny thing about loops is that's basically just a map from the interval into your space, well, some nice map from the interval into your space. So you can compose them actually, right? But if you rescale, you can just compose them. My first loop would go from 0 to 1, and well, I could let my second loop go then from, I just use this notation here, from 1 to 2, and then I just rescale the whole thing, and I get another loop from 0 to 1, and I shouldn't overlap my own picture, right? So concatenation of loops gives you another loop. And that's a multiplication rule. And if you have a multiplication rule and you're an algebraist, then you're in business. Then you basically have something like a group or something like that. And indeed, you have a group. So there is a unit, for example, and the unit is always the one you forget if you see it for the first time. But a totally legal loop is a loop that doesn't move at all. I just stay at my chosen base point. I don't move at all. And of course, if I compose that to any other loop, the original loop doesn't really change. So this is actually a unit in this multiplication of composition of loops. And the move backwards, I will show you an animation in a second, is the inverse. So actually, it's not hard to check that this fundamental group is actually a group. But now that you're in business, because you have turned information about the space, might be a complicated space. You have no idea how it looks like or whatever. You have turned it into a object of combinatorics, object of algebra, into a group. So let's have a look at the animations actually. So here are the two animations that I, as I said, stole from a certain website. It's linked below. The website has really nice animations. So as you can see, I have on the left-hand side, my space X, and that's the loop. So the loop goes around once, and if you just go around in the other direction, it's actually the inverse loop. You could, why? Because you can now contract it, as you can see in the left animation, right? You go around once, you go around the other way, and you contract it away. And as I just told you, the do nothing is the unit. So this is actually the inverse. So going around clockwise, which is the first part of the animation, you can undo it by going around counterclockwise. And on the right-hand side, you see basically animated how this equivalence of loops looks like. You start with a pretty crazy loop, and you can contract it until it looks relatively simple, but you can't contract it down to the do nothing loop. It's not trivial because you kind of get stuck at the hole. And that's the whole idea of this fundamental group. You just imagine now you have a more complicated looking space and you try to compute this group. And again, that's the whole point. You get a group in the end, right? A group, an object of algebra. Right, as I say it again, because this website is really nice. So you have the link to other animations, not just the fundamental group, but also more animations for the fundamental group in the description. But anyway, so algebraic topology, the study of topological object shapes using algebra. And what you usually classically learn is there are basically two major topics. There's a black one and there's a red one. And then certainly generalizations, I will talk about them in a second. But basically you have two different topics. Something like fundamental groups, you call them homotopy groups. And they are basically the same idea. They're pretty easy to explain, but they're sometimes ridiculously hard to compute. Even homotopy groups of the easiest topological objects like spheres are not that simple to compute. Right, the sphere is kind of the easiest, not completely trivial object you could imagine. And even for those, they're not so easy to compute. On the other side, I have those things that are called homology. And they are really good. They're easy to compute, but they are not so easy to explain. It takes you a while to digest what they actually are. So the homotopy is more like you take analogs of loops, so analogs of the fundamental group, just higher dimensional ones, basically. As I said, relatively easy to explain, but hard to compute. Homology is a bit trickier. You would like to do something like simplicial or singular homology. You will learn all of that in a standard class on algebraic topology. What is less clear, and that's what I like to stress immediately in the first video, if you see those two, so kind of the natural one, the black one, so let me make it black actually. The natural one, the black one, and the slightly strange one, the red one, they're of course related, and you will learn how they are related. But it turns out that in particular, the last one has really nice generalizations, which are then collected in some kind of categorical or homological algebra. And this homological algebra turns out to be a subject on itself. It's motivated by topology, but it is way more general. I show you an extremely nice application of the ideas of homological algebra. So in the end, the ideas of topology on my last slide. The other one also has a generalization, which is also very popular. It's called homotopical algebra, homotopy type theory, something like that. But it's much more complicated and less classical as homological algebra. So in a class on algebraic topology, what you should see is those two different aspects of translating topology to algebra. The first one is more about groups. The second one is more about vector spaces, if you want. And then some certain generalizations of it, like statements that actually are more part of real algebra in the sense that they are part of homological or homotopological algebra. Okay, to wrap up, let me give you two applications of topology, one very classical and one very recent. And the second one is really amazing. The first one is also very amazing. I shouldn't diss the poor first statement that you see right now. But as I said, it's pretty classical. So it's a question, how can you prove actually the fundamental theorem of algebra? Do all non-constant polynomials actually with complex coefficients have roots? The problem about this whole question is that roots are extremely hard to compute. So basically you can do nothing if you have a random polynomial to compute the roots. You can kind of approximate them, but really compute them, that's a pain. So you might expect that the proof of the statement isn't all that easy. And there are various proofs. Actually, it's one of the theorems in mathematics which has the most known proofs. So some people collect proofs of the fundamental theorem of algebra. Here's one. You can actually use what I just told you about the fundamental group to prove the fundamental theorem of algebra. And it's just a coincidence that this is also called fundamental. So the fundamental group and fundamental theorem of algebra a priori don't have anything in common. Anyway, the only thing you need to know is kind of that the group associated to the disk with a hole is the easiest infinite group you can imagine. It's the integers with addition. And then you can play some tricks. Then you basically do a proof by contradiction is not hard. It consists of two steps. Basically, you assume that f has no roots. You rescale it until you get a function on the circle, and you count some winding numbers. And under the assumption that it has no roots, you can contradict. You get a contradiction. The link to the formal proofs in the description is not very long. It's about 20 lines, maybe 25. It's not too bad. So actually, if you know a little bit about topology, you can prove something that a priori doesn't have to do anything with topology, which is kind of fun. So what I just told you is that you can prove a statement in algebra using the translation from topology to algebra. So it's actually a two-way street, right? So it's not like, okay, the main idea is I would like to translate topology to algebra and then come back the whole way. But it also is a two-way street. So you can also say something about algebra using topology. Okay, second application, which eventually will end in a video, I guess, is it's really, really new, a really, really new idea. It's called topological data analysis. It's one of the main booming fields of mathematics right now. It's a ridiculously simple idea. If I tell you about it, you will immediately understand that this is important. I show you an application in a second, or actually 3 real-life applications in a second. But it took a long time to come up with it because kind of it's this idea of applying what I just said, homological algebra to a more general context. So homological algebra really made it into standard mathematics in about the 40s or the 50s of the last century. And then it took a little bit longer to make it into other fields like computer science. So topological data analysis is very useful in computer science, for example, but also neurobiology or sociology. So it's really nice. It just takes a while. And the idea is as follows. The idea is pretty simple. So life gives you data. So here you see data. And data are just points. You measure something, you get a point. But actually, life gives you data, and data seems to have shape. And topology is, well, the whole slogan of topology is that shape matters. So just put both together, and you get what is called topological data analysis. For example, so this set of data points, it certainly seems to arrange themselves in a circle, but it has some other little clusters like this one. Maybe this one is a little bit clustering here. And maybe this one is a bit clustering. So how can you actually see this using tools from topology? Well, there is what is called persistent homology, which is an application of the usual ideas that you learn in. It's actually a bit easier than simplicial and singular homology, but it's kind of the same spirit. And it roughly works as follows. So you choose some radius and you draw a circle around all of those points, and you look at how the circles intersect. If they intersect, let's say 2 circles intersect, that you would draw a line between them, something like that. You would do that for all points. Here's an example on the right-hand side. And then you get one of those objects here, right? So you get one of those objects, like this one. And then you can try to apply topological methods to it. And this persistent homology is basically measuring how your space depends on your choice of D. So you can vary D. Of course, if D is very, very small, like you don't see anything, everything will just be an isolated universe. If D is very, very big, then everything is just clustered and connected. And kind of this persistent homology measures how the data changes as D goes to infinity, basically. So let me show you a very nice talk, or slides from a very nice talk linked in the description, about topological data analysis or topology, or this idea of topology in general, which is certainly way better than anything I could ever do. So let me just show it to you. And it also highlights 3 main applications of topological data analysis, which really stunned me when I saw them for the first time. So here you go. Those are the slides, freely available, linked in the description. And I would like to, it's really long. It's 67 pages. And yeah, let me just jump to one of them. So here, so there's persistent homology. And he explains basically what that is. And it gives 3 main applications, which it's very stunning that you can apply ideas from some pure field like topology to actually real life. So one of them, and he quotes really existing papers. So this is really honest research that is done in this direction. So there's an application to points on shapes. So this is a usual diagram we would draw. There's an application, maybe this makes more sense from what I've told you. So there's an application to collaboration networks, because of course, in some sense, you can think of this, let's say this is on a topological object like the Earth, and maybe it matters more, it matters not just how they are connected, but in what close sense they are connected. So here's a cluster, and you would pick up, for example, this little cluster here very quickly if D goes up, and here's a cluster and so on. And the final application mentioned on this slide is to brain networks, which shocked me a lot. But apparently in brain networks, you can do the same trick. You can just look at basically clusters, and you can use this persistent homology to say more about brain networks, which is definitely a very important application of this idea of topology. Right. So that's basically what I wanted to tell you today. Let me wrap up. So in a classical course on algebraic topology, you should see those 2 sides of algebraic topology. Let me call it the really classical one, homotopy, fundamental groups in one way or the other. And then the more modern one, which is already very classical because it's at least 100 years old, something like that, which would be homology. And in particular, homology is extremely applicable to the real world. Homotopy at one point probably will also be very applicable to the real world, and it's already used in other forms like homotopical algebra. But homology seems to be, at least from my perspective right now, seems to be the more applicable thing. And the main difference between them, there's obviously relation, but the main difference is one of them, you explained it and it makes sense immediately. And then I ask you to compute it, or you ask me that I should compute it, and I would have no idea what to do because it's just pretty hard. The other one, it takes a little while. It's not super bad, if explained correctly, it's not super bad, but it takes a while until you understand it. But as soon as you get going, it's actually pretty easy to compute. In particular, you can ask a computer program to do it in most cases, or let's say in some cases. And that's the whole idea of a classical course in algebraic topology. As I said, algebraic topology is a translation from topology to algebra. And at one point, you might like even the algebraic part a little bit more, and you might guide your algebra using topological ideas. And you would end up with something like homological algebra or homotopical algebra. This is kind of the last thing you would see in a class on algebraic topology, or at least in a standard class on algebraic topology. The main source for algebraic topology, if you want to learn more, is Hatcher's freely available book, linked in the description. And I really would like to have you look at it. It's really, really good, at least in my opinion. I do like it. Anyway, I am already starting waffling. So let me just say, I hope you enjoyed the video, and I also hope to see you next time.